Okay, welcome to the deep dive. Let's think about rain for a second. Where does it go?
Right, because it really depends, doesn't it?
Totally. I mean, if it's falling on, say, a forest floor, it acts one way. But if that same rain hits a parking lot, it behaves, well, very differently.
A completely different path.
And that's what we're diving into today. That difference, it's kind of a hidden consequence when we change the ground, paving things over. And we have this simple calculation that's going to make it startlingly clear.
It really lays bare how a seemingly small decision, what material do we use for this surface, can have this pretty significant impact on, well, how much water just runs straight off an area.
Yeah.
It's a shift in the natural water cycle.
Exactly. So for this deep dive, we're using a specific example, a hypothetical but a useful one. What happens if a piece of land in Fayetteville, Arkansas gets converted? Goes from being a forest to a brick parking lot. And our mission really is to use this tool, it's called the rational method, plus the specific data we have for this Fayetteville spot to figure out just how much the peak water flow actually changes.
Yeah, and the numbers, they really do tell a story, a pretty compelling one, about these sort of unseen effects of development. So let's talk about this tool, the rational method.
Okay.
It boils down to a formula, Q equals C equals I EA. Simple looking but powerful. This is our main equation for figuring out that peak discharge.
Right. Q equals C times I times A. Let's unpack that. What does each letter mean? Because each one's obviously a key part of this picture.
So Q, that's the peak discharge. You can think of it as the maximum rate water flows off that specific area during a rainstorm.
Yeah.
The biggest rush of water.
Peak flow.
We usually measure that in cubic feet per second, or CSS.
Okay, Q is peak flow rate in CSS. Got it. Now, C, you mentioned surface materials. This feels like the important one for today's example.
It absolutely is. C is the runoff coefficient. Now, this isn't a unit like feet or seconds. It's just a number, usually somewhere between 0 and 1.
Okay.
It basically tells us how much the rain that hits a surface turns into runoff, meaning it flows over the surface instead of soaking in.
Ah, okay.
So a low C means the surface is absorbent like a sponge, or it slows the water way down. Think forests, fields. A high C means most water just zooms right off, like pavement.
So C is like how runny the surface gets in the rain. High C, lots of runoff. Low C, not so much.
That's a good way to put it, yeah. And this is where you see the huge difference between natural ground and, built surfaces.
Makes sense. Okay, what about I?
I is simpler. It's the rainfall intensity, just how hard it's raining, typically measured in inches per hour for this formula.
Right, inches per hour. And the last one, A.
A is just the area, the size of the piece of land we're looking at. And crucially for this method, it needs to be in acres.
Acres. Okay, good to know. So Q equals CX IXA. Peak flow equals how runny the surface is times how hard it's raining times the size of the area in acres.
You got it.
Perfect. Now let's apply this. Our Fayetteville example. We've got the data. The rainfall intensity I is given as 2.0 inches per hour.
Yep, and conveniently, the units are already correct for the formula, inches per hour.
Nice. Saves a step. But the area A, you mentioned it needs to be in acres. The data says our site is 10,000 square feet.
Okay, so yeah, we got a conversion to do. Can't just plug in 10,000. The rational method is specific about needing acres for A.
Right, and we have the conversion factor here. 1 square foot is equal to 2.2957 times 10 to the minus 5 acres. Tiny number.
It is. So you take the 10,000 square feet and multiply it by that tiny factor.
Okay, 10,000 times 2.2957 E5. Let's see, it gives us 0.23 acres.
Exactly. So 0.23 acres, that's the A value we'll use in our QCIA calculation for both the forest and the parking lot.
Okay, A is 0.23 acres. Now let's get to those C values, the runoff coefficients. This is where the forest and the brick parking lot really part ways, right?
This is the core of the difference, absolutely. So first, the forest, the source material, actually gives a range for the C value, from 0.15 up to 0.30.
A range. Okay, so what do we do with that? We need one number for the formula.
Yeah, good question. When you have a range like that, you often have to make a reasonable assumption. And what's done here is they take the average.
Makes sense. So average of 0.15 and 0.30, that's 0.15 plus 0.30 divided by 2, which is 0.225.
Precisely. So C for the forest, C forest will use 0.225. And it's good practice, like we're doing now, to state that assumption, that we use the average.
Right. C forest equals 0.225. That feels quite low, what you'd expect for a forest floor, right? Lots of soaking in.
Definitely. Now compare that to the brick parking lot.
Okay, what's the C for brick?
For the brick surface, the value given is 0.85, much higher.
Whoa, yeah. 0.225 versus 0.85? Big jump.
Big jump. And it's actually interesting. The source notes that even brick at 0.85 is considered less hydrologically intense, meaning less runoff than materials like asphalt or concrete.
Really?
Yeah, those can have C's values up around 0.95. Almost all the water runs off immediately.
Wow. Okay, so even among paved surfaces, there's a difference. But still, 0.85 for brick is worlds away from 0.225 for the forest.
Absolutely worlds away. And now, look, we have all our pieces. We've got C for both surfaces. We've got I, the rainfall, and we've got A, the area in acres.
We're ready to calculate Q for both scenarios.
Yeah, so let's plug them into Q, the CXIXA. First, the forest.
Okay, forest time. What did that natural system look like in terms of peak flow?
So for the forest, C is 0.225, I is 2.01 inches per hour, and A is 0.23 acres. Calculation is Q forest equal 0.225, 2.0.23.
All right, 0.225 times 2 times 0.23. That gives us 0.103.
0.103 cubic feet per second. That's the peak discharge Q forest.
Okay, about a tenth of a cubic foot per second flowing off that nearly quarter acre of forest at the peak of this rain event. Seems manageable.
Relatively low, yeah. Now, same process for the brick parking lot. Remember, I and A stay the same, only C changes.
Right, so now C is 0.85, I is still 2.0, A is still 0.23, so Q brick equals 0.85, 2.0, 0.23.
Okay, and punching those numbers in,
Wow.
0.85 times 2 times 0.23 gives us Q brick equal 0.390 cubic feet per second.
0.390. Wow. Okay, just hearing those side by side. 0.103 CFS for the forest and 0.390 CFS for the brick parking lot. That's almost 4 times higher.
It's a huge increase. It really highlights the impact of that surface change.
So it's not just a little bit more water running off, it's significantly more and presumably faster too.
Exactly. And the really key number for understanding the impact of this land use change is the difference between these two. What's the actual increase in peak discharge? We call that Q delta Q.
Delta Q, the change. So you just subtract the forest value from the parking lot value.
Yep, Q brick Q forest.
Okay, at Q 0.390 minus 0.103.
Which gives us Q 0.287 cubic feet per second.
0.287 CFS. So making that switch, forest to brick parking lot, adds an extra 0.287 cubic feet per second to the peak flow coming off that specific piece of land during that specific rain.
That's the takeaway number. An increase of 0.287 CFS.
Why? I mean, intuitively we know pavement means more runoff, but what's the mechanism? Why such a big jump?
It really comes back to that C's value difference and what it represents physically. In the forest, you've got, the soil, the leaf litter, plant roots. It's like a natural sponge.
Right.
Slows the water down, traps some of it, and critically allows a lot of it to soak into the ground. That's infiltration.
Okay.
On a hard surface like brick, which might have tiny gaps, most of that water simply can't infiltrate. It hits the surface and whoosh, it sheets off, becomes surface runoff almost immediately.
And that quick runoff is what leads to the higher peak flow.
Exactly. Less soaking in means more flowing off and faster.
And the source material connects this increase directly to infrastructure, doesn't it? Like pipes and ditches.
It does. Because think about it. That extra 0.287 cubic feet per second of water has to go somewhere. Any drainage system like culverts under roads or stormwater pipes designed for the forest condition now has to handle this significantly higher peak flow rate.
So if the drainage wasn't designed for that extra flow, problem.
Big problems, potentially. You risk overwhelming the system. That can lead to localized flooding right there.
Yeah.
Or increased erosion downstream carrying pollutants. It cascades.
So this single small-ish example, this hypothetical quarter-acre lot, it really demonstrates a much broader pattern, doesn't it? How traditional development, swapping absorbent nature for hard surfaces, fundamentally messes with how water moves.
It absolutely does. Increases runoff, decreases that vital infiltration that recharges groundwater. It's a major shift.
And this is why we hear about alternatives now, right? The
Right.
source mentions things like green roofs or porous pavements.
Porous asphalt, permeable pavers.
Yeah, or things like rain gardens, bioretention cells, ways to try and counteract this effect.
Exactly. Those are all strategies aimed at trying to mimic some of that natural water absorption and slowing down process within developed areas, trying to lower that effective C value, essentially.
We won't dive deep into those solutions today, but seeing this calculation makes it really clear why people are looking for those alternatives.
Definitely. The core point here is just how profoundly changing the ground cover, even on a seemingly small scale, redirects the path of water.
Yeah, and that number, that increase, 0.287 cubic feet per second, it might sound kind of abstract or small maybe.
Perhaps on its own.
But then you scale it up. Think about, I don't know, a huge shopping center parking lot, 50 acres. 100 acres, or just add up all the roads, roofs, and driveways across an entire city. That small increase per square foot suddenly becomes this colossal wave of extra water during a big
A
storm.
massive volume that our pipes and rivers have to somehow manage or, well, fail to manage.
Which really brings it home.
So maybe a final thought for you listening out there. Now that you've seen this, now that you understand the power hiding in that C's value, that runoff coefficient, how does that change how you look at the world around you?
Yeah, like when you walk outside later.
Right. That patch of grass versus the sidewalk next to it, the roof overhead versus the trees in the park. Knowing what you know now about how water interacts differently with each, what questions does that raise for you about the choices we make and how we build our communities?